Hello everyone, and welcome to a new video from Via Doctus. Today, we'll be discussing geology, the science that studies the Earth's composition, structure, dynamics, and history, covering everything from natural resources to the processes that impact its surface, and therefore us humans. To begin our discussion on geology, we'll start with minerals and rocks, elements that are very common in our lives, but that we rarely stop to think about. Let's start with the basics. What is a mineral? A mineral can be defined as a naturally occurring substance that is stable at room temperature, is usually inorganic and solid, has a defined chemical composition, is abiogenic, and also has a certain crystalline structure or ordered atomic arrangement. If you think about it, the definition of a mineral might seem somewhat ambiguous, and the truth is that in mineralogy, the branch of geology that studies the physical and chemical properties of minerals, the exact definition of what a mineral is can be a subject of debate, especially regarding the requirement of being abiogenic. In other words, a mineral must be formed from material that is not produced or influenced by living organisms. However, some minerals are often biogenic, such as calcium carbonate, which typically forms from the sedimentation of coral skeletons and seashells on ocean floors. Additionally, living organisms often synthesize inorganic minerals, such as hydroxyapatite, a calcium phosphate that is always with us as it makes up the enamel of our teeth, the hardest component of our entire body. Setting aside the abiogenic question, minerals must also be in a solid state, so they cannot be liquid or gaseous at room temperature and pressure. For example, liquid water would not be considered a mineral, but ice could be. Because of issues like these, it's clear that there can be difficulty in certain cases in determining what qualifies as a mineral, which is why some experts propose not requiring that minerals be solid to be classified as such. As you can see, the definition of a mineral is a topic that sparks various controversies, even among scientists. Currently, there are more than 5,300 types of known minerals, most of them approved by the International Mineralogical Association. Additionally, new minerals are continuously being discovered, approximately 50 to 80 per year, so the list keeps growing. Now that we have defined what a mineral is, we can move on to define what a rock is. We could say that any solid material composed of one or more minerals, or even other materials that are not considered minerals, can be called a rock. Additionally, rocks, unlike minerals, do not have a defined chemical composition. It's also important to note that rocks do not always have to be composed of hard materials. They can also be made up of soft materials, such as mud or clay. Having more or less defined what minerals and rocks are, we can move to a much larger scale, as the Earth's crust is primarily composed of these elements. Specifically, silicon and oxygen make up approximately 75% of this crust on which we live, leading to the predominance of silicate minerals, which constitute more than 90% of the outermost layer of our planet. As you can imagine, the thickness of the Earth's crust is not uniform, varying between 3 miles deep at its thinnest points and 43 miles deep where it is thickest. The thinnest parts make up the oceanic crust, which underlies the ocean basins and is composed of dense igneous rocks, mainly made of magnesium and iron silicates, like basalt. In contrast, the thickest crust is the continental crust, which is less dense and composed of aluminum, potassium, sodium silicate rocks, such as granite. Additionally, we know that many rocks that now form the Earth's crust were formed less than 100 million years ago. However, the oldest known mineral grains are approximately 4.4 billion years old, indicating that the Earth has had a solid crust for practically its entire existence, except during the early stages of the planet's formation in its first 200 million years. Understanding the Earth's crust would be very difficult without knowing the internal structure of our planet, from which the vast majority of the minerals and rocks we know originate. And we say the majority, and not all, because, according to a study published by Earth and Planetary Science Letters, every year, about 5,200 tons of space dust particles, or cometary and asteroid fragments, fall to the Earth's surface. Just below the Earth's crust, the mantle extends to a depth of 1,800 miles, making it the thickest layer of the Earth, and it is divided into the upper and lower mantle. The mantle is composed of silicate rocks that are richer in iron and magnesium compared to those of the Earth's outer crust. Although the high temperatures of the mantle exceed the melting points of rocks, if they were on the surface, the mantle is almost exclusively solid. This is due to the enormous pressure exerted on the rocks, which prevents them from melting into a liquid state, as the temperature at which they begin to melt increases according to the pressure they are under. Additionally, the high temperatures within the Earth's mantle cause this silicate material to be malleable enough to flow over extended timescales. This slow flow causes the displacement of tectonic plates. Furthermore, as one moves deeper into the mantle, the pressure increases significantly, so the lower part of the mantle flows with less ease than the upper mantle, with its viscosity varying depending on the depth at which it is measured. Below the Earth's mantle, we find the outer core, consisting of a plasma layer that is assumed to be primarily composed of liquid metal, based on scientific evidence provided by seismic waves. This layer is made of iron mixed with nickel and other lighter elements, with scientists suspecting that approximately 10% of it is composed of oxygen and sulfur. These elements are believed to have been abundant in the protoplanetary disk that gave rise to the Earth, and also dissolve easily in molten iron. The temperature in this layer of the planet's core varies from 8,000 degrees Fahrenheit in its upper region to 11,000 degrees Fahrenheit in its lower region. Most scientists believe that convection in the outer core, combined with the Earth's rotation, generates the Earth's magnetic field through a process explained by the dynamo hypothesis. This is because the Earth's outer core is an electrical conductor, and convection currents occur within it since it is mostly composed of liquid metal, creating a vast dynamo that maintains a system of electric currents that generate the magnetosphere, or Earth's magnetic field. This magnetic field is crucial for the evolution of life on our planet, as it protects us from harmful solar radiation and cosmic rays. Lastly, there is the inner core, the innermost geological layer of Earth, primarily consisting of a sphere made mostly of solid metal, an alloy of iron and nickel with some other elements. It has a radius of approximately 758 miles, which is almost 20% of Earth's radius or 70% of the Moon's radius. The temperature at the surface of the inner core is estimated to be around 10,000 degrees Fahrenheit, roughly the same as the surface temperature of the Sun, although this is still hundreds of times cooler than the 27 million degrees Fahrenheit generated by nuclear fusion processes in the core of our host star. You might wonder why the outer core is liquid while the inner core is solid. The reason is that iron can remain solid at such high temperatures because its melting point increases dramatically under the immense pressures of millions of atmospheres it experiences. While it may not be solid in the way we understand solids on the Earth's surface, because it lacks movement or convection processes, it does not behave like a fluid. Furthermore, although seismic waves propagate through the inner core as if it were solid, measurements cannot easily distinguish between a perfectly solid material and one that is extremely viscous. Scientists also believe that the Earth's inner core is slowly growing as the liquid outer core cools and solidifies, a process driven by the gradual cooling of the Earth's interior. This cooling is estimated at approximately 180 degrees Fahrenheit per billion years, but there's no need for alarm, as this cooling process is extremely slow due to the large size of our planet, something that did not happen with smaller planets like Mars. The square-cube law tells us that as an object increases in size, its volume increases faster than its surface area, which is why Mars has lost internal heat at a much faster rate than Earth. Recent studies also suggest that, despite still being in a liquid state, there is little to no movement or convection in Mars' core, resulting in its current magnetic field being practically insignificant. This has left the planet without the protection it once might have offered to any potential microbial life millions of years ago, if such life ever existed on Mars. Now that we know what rocks are made of and where they come from, how do we classify them? Well, leaving aside meteorites, there are three main types of rocks, depending on how they were formed in the different layers of the Earth: sedimentary, igneous, and metamorphic. Geological processes that take place on the Earth's surface cause changes in topographic relief that are imperceptible on a human timescale, but reach considerable magnitudes when observed over geological timescales of millions or billions of years. For example, the relief of a mountain will inevitably disappear due to the erosion of its rocks. The history of a sedimentary rock begins with the erosion and alteration of pre-existing rocks, resulting in tiny particles and fragments that are usually transported by river water, ice, wind, or ocean currents to areas far from their origin. These materials eventually accumulate, forming sediments that are deposited in layers or strata. This process also occurs due to the activity of living organisms, such as coral reefs that turn into limestone, a biogenic sedimentary rock, forming layers that are compressed until they finally harden into rock. Examples of sedimentary rocks include limestone, gypsum, coal, and sandstone. In contrast to sedimentary rocks, igneous rocks are formed through the solidification of lava from volcanoes or magma that cools inside our planet. It's important to remember that the distinction between magma and lava lies in their location. When geologists refer to magma, they mean molten rock that is still trapped underground. If this molten rock reaches the surface and continues to flow as a liquid, it is called lava. Due to their formation process, igneous rocks contain volatiles and dissolved gases. Examples of igneous rocks include basalt, granite, pumice, and obsidian. Lastly, we have metamorphic rocks, which are formed when igneous, sedimentary, or other metamorphic rocks are subjected to an environment that is energetically very different from the one in which they originally formed, such as much higher or lower temperatures, or significantly different pressure. Metamorphic rocks are especially common in the deep areas of the Earth's crust, above the magmatic base, where they are formed from the enormous heat and pressure to which they are subjected. These rocks are usually hard and often contain crystals and distinct layers. Examples of metamorphic rocks include slate, marble, quartzite, gneiss, and schist. With this, we complete our brief tour of the elemental geology of our planet. In future videos from Via Doctus, we will continue explaining more interesting aspects related to geology. But for now, this is where today's video ends. If you enjoyed the video, don't forget to give it a like and subscribe to the channel. Thank you very much for watching and see you in the next one.